Okay, so next up, we're going to take a look at 9.2. We are going to have a relationship between pressure, between volume, and temperature. So again, I'm just going to write this down really quickly. We are going to have a relationship between pressure, volume, and I'm going to write the ideal gas law. You don't have to write this now, but we're going to write it later. PV equals nRT. So we're going to have a relationship between pressure, volume, and as always, moles, or quantity in this case. So quantity, because we can convert moles to grams and so on and so forth. And then T, which is going to be in temperature. By the way, temperature always in Kelvin. Pressure can be in any pressure unit as long as you're in equal pressure units. Volume can be, is typically in liters, liters for gases, and then moles, again, grams, moles, whatever. We're going to have to do some stoichiometric conversions at some point. So we have a bunch of different laws, and we're going to have a combined gas law. But it's important to recognize kind of how these things work independently of one another. So Boyle's law, we're going to start with Boyle's law. There is going to be a mathematical relationship between these things. So Boyle's law is pressure and volume relationship. So when pressure and volume are being analyzed, those are the two variables. That means we are at constant temperature, and by the way, and moles. So the moles remain constant as well. Generally, we're going to ignore moles from now on. We're just going to assume we're having a constant moles, but we should include that as well. So Boyle's law, pressure and volume relationship. So here in my little demonstration, I have a container. And that container has X number of gas molecules or X amount of moles of gas. If I add some weight, what we expect to see is that basically just adding force to the top. So we have increase the amount of force that we're pushing down on. Okay, so what we have done is essentially changed the pressure. So is pressure in the second step higher or lower? So is pressure 2 higher or lower than the same as pressure 1, and why? In this case, pressure 2 is higher. Again, pressure is going to be the amount of force exerted by the gas molecules on the container and on all of the walls. Pressure is higher because we're seeing a decrease in volume. Volume is decreasing. So the relationship, the mathematical relationship between these two is P1 V1 equals P2 V2. The relationship between those are as volume goes down, as we decrease volume, we're going to see an increase in pressure, okay? Or volume is, to write it properly, inversely proportional to pressure. Okay, so this is the important part here. Pressure P1 V1 equals P2 V2. So if the volume goes down, okay, the pressure has to go up. Again, if we looked at this, if my volume is going to decrease, that means if my volume goes down, that means pressure has to go up because they have to be equal to one another. Okay, so those are inversely proportional. One goes down, the other one has to go up. That is Boyle's law, the relationship between pressure and volume. And we're going to go through a bunch of examples for this. All right, let's take a look at Charles' law. Charles' law is looking at the temperature and volume relationship. So here we have V1, T1, one weight on top. So we haven't changed the pressure at all. We have just heated it up. Okay, so by heating it up, we're at constant pressure and constant number of moles, so the same number of moles. What we see here is the gas molecules are moving, okay? But as soon as we heat it up, they're moving, those arrows are much longer, they're moving much faster, and they're moving much faster. Okay, so what ends up happening is we notice that there is an increase in volume. So is V2 higher than V1? Yes, there is an increase in volume. We see an increase in volume because of the increase in motion, okay? So because of the increase in temperature. These two things are directly proportional, okay? So they're directly proportional to one another, meaning if I increase the temperature, I see an increase in volume. By seeing an increase in those two, they are directly proportional to one another. So increase in T again. So T is proportional directly proportional to V. So the mathematical relationship, because again, that's the important part, the mathematical relationship between these two is V1 over T1 is equal to V2 over T2. I'm hoping at the end of this, you have to remember one formula and should be able to derive the rest of these. So you don't have to keep memorizing all of these relationships. But the V1 over T1 equals V2 over T2. Again, that's because we're increasing the heat. They need a little bit more space and they're just gonna kind of bump up that container. All right, next up is the Gay-Lussac law. Gay-Lussac law is pressure, temperature, constant volume. So we put more weight on here to make sure that basically we've maintained the same pressure. So now what happened, or I'm sorry, we've maintained the same volume, I should say. So here we're going to, again, we're going to increase by increasing the temperature. Because volume cannot increase because we forced it to stay the same, we have seen an increase in pressure instead. These things are pushing harder against the walls because they're moving faster, and therefore we see that is P2 higher? Yes, P2 is higher. We see an increase in pressure because of the increased motion, because of the increase in temperature. So these two things are directly proportional to one another. Temperature is directly proportional to pressure. So the relationship is much the same as it was for the one above. Pressure and temperature, P1 over T1 equals P2 over T2. Okay, so again, pressure relationship between the two, pressure and temperature relationship, by having a constant volume, we see an increase in pressure. Great. Okay. Now we finally introduce the idea of Avogadro's law. So every single one of these has been a closed system. We either heated up, we changed the volume, we added pressure, we did something like that, but we didn't change any of the volume relationships. So Avogadro's law, we're now going to keep constant temperature, constant pressure, and we're going to see what's going to happen. So here we see that the volume changes. By removing half of the molecules, we actually see half of the volume is going to change. So by decreasing, in this case, by decreasing the number of moles, we see a decrease in volume. Those two things are directly proportional to one another, meaning, again, we have the relationship V1 over N1 is equal to V2 over N2. And they're in fact directly proportional. So if I have the number of volumes, I'm going to have the number of moles. The most important thing about all of this is the type of gas, as in neon or H2 or something large like Cl2 will not matter. Because there's so much space in between them, the type of gas does not matter. Every single gas is going to behave the exact same. In fact, at standard temperature pressure, which we're going to talk about shortly, at standard temperature pressure, and this is an important number to know, 1 mole of gas is equal to 22.4 liters of any type of gas, is equal to 22.4 liters. So we see the relationship between volume and moles. So that means if I know volumes, I also know moles. And this value of 22.4 liters, which is an important number to know. Okay. So there we go. There we have it. We have all of the relationships between volume, temperature, pressure, and moles. So we can actually just create a combined gas law. So I'm going to write it out first, the combined gas law, and highlight it so you can kind of memorize it if you want to, but you don't need to. So P1 over V1 is equal to N1 over T1, all equal to P2 over V2, all over N2 over T2. So this is the combined gas law. If you are going to change. Basically, what's going to happen is you can always use this. If something is kept constant, you're just going to remove it. So if we're do some problem that's at the same pressure, just remove the pressure component completely and just solve for what you need. A couple of important things for this though: temperature must be in Kelvin. So don't screw around with that. Temperature has to be in Kelvin. The volume and the pressure units must match. You can actually use any pressure or volume unit you want as long as you're using the same unit. Okay, so those will not matter because if you're using the same unit, generally they're going to cancel. So you must use the same unit. So let's show the derivation of this. Okay, so there's this, that's the result of what I'm talking about. But I'm going to quickly do a derivation of this. So all you have to remember is our ideal gas, PV equals nRT. Again, pressure, volume, moles, temperature, and then you're given this actually, R is your ideal gas constant. The ideal gas constant is in fact a constant. So imagine, so how we're going to solve this is, let's consider that we're in two different states. State one has pressure 1, volume 1, mole 1, moles of whatever state 1 happens to have, R, not 1 because it's a constant, and T1. State 2 is going to have the same thing, only 2. So pressure 2, volume 2, moles at state 2, R again is the same, and T2. So state 1, state 2. So this is going to be state 2. This is state 1. So two different conditions. So I start with state 1, I heat it, I change the volume, I increase the pressure, I do all sorts of things to it to get to state 2, right? So this transition happens. What do we notice is, what we should notice is that R is the same for both of them. So what I want you to do is I want you to solve for R for both of these. So what we're going to have is R is equal to P1 V1 all over N1 T1. And we're actually going to have the same thing for the other side. R is equal to P2 V2 all over N2 T2. Okay. And now all I want you to do is, I just want to set both of these equal to R. So set them equal to one another. So R is equal to P2 V2 equals N1 T2. And R on the other side is equal to, there we go. So that's the relationship that we have there. So these two things are both equal to R. Now all we have to do is actually just set them equal to one another. So I'm just going to take this whole thing and I'm just going to equal them to one another. So we'll get rid of this R. They're equal to one another. Boom. We have the ideal gas law that we have derived. So set them both equal to R, plug them in together, and there you go. So all you really need to remember is this right here, PV equals nRT, because if you know that, you can get the combined gas law and you're good to go. So there's the derivation of it if you ever have to figure out exactly what that combined gas law is. All right, so let's take a look at a bunch of examples. I'm going to let you guys do these. We're going to do these in class. So 1.4 liters of a gas, what's the new pressure? What's the initial temperature? What's the new volume? What's the final pressure? What will the pressure be? And then finally, the ideal gas equation. So the last little bit that we're going to talk about is the ideal gas equation. So we just talked about it, so I'm going to talk about it again and again and again. PV equals nRT. Okay, so PV equals nRT is the ideal gas equation. That's the one that you need to know. Let's take a look at the derivation. So what we know, just in terms of volume, we know that volume is proportional to temperature. I know that volume is proportional to inversely proportional to pressure. I know that volume is proportional to moles. All of this can be combined together to give me volume is proportional to moles temperature over pressure. How do we get rid of a proportionality constant? Again, proportional doesn't tell you the exact number of, it's not equal, right? Volume goes up a little bit, temperature has to go down or has to go up as well, but it doesn't give you the exact number. So in order to transition from a proportionality to an equal sign, we basically are going to include a constant. Okay, so the changing from a proportionality to an equal sign to an actual equation, you basically just have to include a proportionality constant. Okay, and that goes for physics, it goes for anything. Okay, NT all over pressure. So volume is equal to R times N times T all over pressure. Okay, so yeah, this is a great start. We know that we can just rearrange this now, and what do we end up with? Well, we end up with the equation that we know and love. Pressure times volume is equal to nRT. There we go. So we've done it. We have essentially derived it all based on our proportionality. So the R is the proportionality constant. R is equal to 0. Let me do this right. 0.8206. The units are really important. Liter atmospheres per mole K. Okay, this is known as our ideal gas constant. This is not the only ideal gas constant that we're going to have. We will have another one where energy is going to be involved, but this is my ideal gas constant. So one really quick thing about this, please, please, please recognize that units are important. Make sure the units, whenever you use this, make sure units match. Units must match. So if you're doing something with the ideal gas law, you have to include with the ideal gas equation, you have to make sure that you have liters, atmospheres, moles, and Kelvin for all of your units. Otherwise, it's not going to work out and you're going to get that wrong. So please, please double check and make sure that you get that. All right, so this is what we have. PV equals nRT, and we know our R value is the constant that makes it go from a proportionality into an equal sign. And then the last little bit, standard temperature pressure, I think that's it, yeah. Standard temperature pressure. Standard temperature pressure, we have to have kind of a standard temperature and pressure that we look at. So standard temperature pressure. Our standard temperature is going to be 0 degrees Celsius or 273 Kelvin, okay? Our standard pressure is 1 atmosphere or 760 torr. Again, millimeters of mercury. Okay. It's important to, it does not equal delta H naught, where we had this idea of the standard state. The standard state was at 25 degrees Celsius and 1 atmosphere. Okay, so we really can kind of ignore this. This is the important part of this. We can ignore the idea of the standard state is different from standard temperature pressure. Standard state is at 25 degrees Celsius, 1 atmosphere. And we see delta H naught, delta S naught. We're going to see that in like our basics, not delta S, just S naught. But our enthalpies were all in standard states of 25 degrees Celsius and 1 atmosphere. So we have to make sure that we are knowing the difference between standard temperature pressure and standard state. Those two things are in fact different. So do these problems as well. This is the longest part of the, yeah, these are all the problems that we're going to do in class. All right, good.